My name is Selim. I'm a researcher at PEER, and I'm mainly here to announce the 2022 last year's PEER blind prediction contest. But before that, I wanted to show a few slides about what a blind prediction contest is, and mainly the PEER blind prediction contest. So to start with the definition of a blind prediction contest, basically this is a competition in which participants make predictions of physical phenomena without knowing the results. And in earthquake engineering, it is used, and it is mostly used for predicting the results of large-scale experiments, mainly using analytical models. And in this blind predictions, the participants who attend the blind predictions are provided with all the necessary information that they can use to build analytical models, such as geometry, like drawings, material properties, measured input motions in dynamic cases, or applied load protocol for quasi-static, and so on. So here in this picture we see the specimen tested and used for the 2017 blind prediction, which is basically a self-centering bridge band. And here, as an example, we provided to the participants the input motions, the geometry, the masses that you see, the results of material tests, and the post-tension details, mainly for the self-centering. And we basically asked them to predict some of the engineering demand parameters, including acceleration of the mass flux or the inertia force, displacement at the top of the column, and overturning moment and other quantities. So beyond this competition aspect, we can consider a blind prediction mainly a community exercise to evaluate and improve the modeling and analysis capabilities of the earthquake engineering profession, both structural and geotechnical. So it has that overarching aspect into that. So then I want to basically continue with this last aspect, mainly asking why blind prediction is important. And if we think about it, considering the methods that are used for the design and assessment of structures, mainly analytical modeling, laboratory testing, and instrumented structures, analytical modeling is the most commonly used method. And as we have seen in multiple presentations today, computation power has been growing exponentially in the past decade. That increases the efficient usage of analytical modeling. So what this means is, as a community, we need to have reliable analytical models in order to be able to make use of these advances. So in that regard, blind predictions mainly inform the current analytical modeling capabilities, identify the modeling areas that need improvement, and also provide guidance how we can improve these modeling aspects that require improvement. So, and then also in relation to performance-based earthquake engineering, which we also heard many times today, it is used to quantify the uncertainty, mainly the epistemic uncertainty of analytical models to be used in probabilistic performance-based earthquake engineering, such as the PEER, PBE methodology. Moving on to the PEER blind prediction contests. Actually, PEER has a long and well-established history of organizing blind prediction contests. It started in 2010, as Professor Mosalam mentioned in the morning talk, with this test initiated by Professor Main, the full-scale bridge column tested at the UCSD shake table. And then there was a break of the blind prediction activities. And then in 2017, we restarted these activities, mainly for the blind prediction from the shaking table test of a self-centering bridge band. And after that year, we have been organizing blind prediction contests every year, 1 or 2 times. And basically, you see summaries of these blind predictions in these boxes here, but they cover a variety of characteristics. So these blind predictions include tests a variety of test types, including dynamic shaking table tests, quasi-static cyclic tests, or monotonic tests. And these are not for only predicting structure response. They include both blind predictions for predicting structural and geotechnical response. As an example, we had this blind prediction that focused on the shallow foundation, the settlement of shallow foundations in liquefied soils, which was a set of tests conducted at UNR by Rami Motamed and the team over there. And as a third aspect, the tested systems include conventional systems and protective systems that we also heard today. As an example of a conventional system, in 2021, there was this test of a reinforced concrete non-ductile gravity column which had shear defects. And also, we heard about rocking systems from David Marr here, and some of these tests included rocking systems and also self-centering systems, which are mainly protective systems. And in terms of the peer community, these also provide some unifying aspects, that these tests were conducted in different peer experimental facilities, including tests at UC Berkeley, UC San Diego, and UNR, University of Nevada, Reno. And also, other than these facilities, there were tests conducted in other laboratories around the world. This test here was conducted in University of Bristol. And in the peer website, there's a dedicated page about the peer blind predictions. So if you would like to get more information about the blind predictions, you can check out this website here. And if you have experimental results that you think you would like to use for organizing a blind prediction contest, please feel free to contact us, and we'll be happy to work with you for organizing the blind prediction contest. And as an example, a peer blind prediction, that is currently planned will be presented hopefully in a few minutes, if I finish on time, by Professor Michael Scott. And this will be mainly wave loading, which would be different than the earlier ones because most of them focused on earthquakes, and this will be tsunami wave loading, so we are looking forward to that. And also we are encouraging the students in the PSC and other graduate students to participate in this blind prediction. And you'll hear more about this from him. And then, as I mentioned, we basically organized several blind predictions over the years, and then we learned useful information from them. And I'll quickly or briefly mention some of these here. And to start with, from the blind prediction in 27, what we observed was for the elastic response predictions, any small error that the participants can have in period or damping values could result in large errors, and this is mainly because of the shape of the response spectra of several ground motions. And considering this fact, there was a recommendation to basically add the natural periods to the list of predicted quantities, such that the source of errors can be identified in a more systematic way in the future blind predictions. And also there was this recommendation to provide the damping ratio to the contestants. And I'll get back to this 2 slides later, which will be my closing slide. And then I mentioned several contributions of blind predictions in terms of improving analytical modeling. So this can be considered as a blind prediction that informed the current analytical modeling capabilities. For the blind prediction in 2018, there was a good finding about settlement, and mainly the observation was the average error of the participating teams in predicting the foundation settlement was lower than the corresponding value for the free field settlement. And this is important because it shows that the utilized numerical tools can predict the foundation response better than the surrounding ground response. And we can consider this as an example of blind prediction that identifies the modeling areas that need improvement, as I mentioned earlier. And the last one that I would like to mention is from the 2019, which is basically an observation about the modeling guidelines and damping, which is a sensitive topic as always. And here, in terms of rocking and wobbling seismic response modeling guidelines, this particular blind prediction contest confirmed that energy dissipation is a key factor that needs to be modeled, but not necessarily through Rayleigh damping. So here, the winner prediction basically predict the results using zero Rayleigh damping and mainly modeled the energy dissipation directly through friction elements. And this can be considered as an example of a blind prediction that provided guidance on improvement of current analytical methods. And these are my last two slides to wrap up, and then I'll announce the winner, which will be the exciting part, hopefully. So talking about the 2020 last year peer blind prediction contest, this was a test mainly a blind prediction contest that used tests performed on the Berkeley Pier 6 degree of freedom shake table in Richmond Field Station. And these tests were conducted in collaboration with Dr. Roberto Andreotti, who was at that time a visiting student at Berkeley, and Professor Bursi from the University of Trento, Italy. And here, mainly, the main motivation of these tests was to demonstrate the effectiveness of a new protective system called impact mass damper that you see here in a lock position. So here, the idea is quite similar to a tuned mass damper. So when the structure moves to the right, when the slider is free to move, it moves to the left, and then it hits the pads of the stopper that you see here, and provides a counteracting impact force. And one may ask, isn't there an issue with this impact force? So here the catch is that this impact force mainly has a higher frequency content and only excites the higher modes of vibration, which basically have lower participating masses. So in terms of dynamic response, it is considered not a major issue. And following this, the structural response is reduced due to this counteracting impact force, which doesn't introduce any additional dynamic effects on the structure. And so, let me see. So here, this idea is reasonable, and it sort of makes sense, but then the final validation would be through testing. That was the main reason to conduct these tests. And so to show the effect of the impact mass damper, basically the tests were conducted in two phases. One with a 3-story steel moment resisting frame without the IMD, and another set with the IMD. And actually, according to the test results, better performance of the system with IMD was shown. And here, I would like to also point out that this moment resisting frame was designed and constructed using Pier's repeat frame. And the repeat frame is this frame that you see here. Mainly, the repeat frame has members that are connected to the clevises using coupons that you may see here, the steel coupons. And these steel coupons are chosen considering capacity design such that the couple moment, ultimate couple moment developed by these coupons are less than the yield moment of the steel shapes, HSS sections or others. In this way, there is never damage to the members, and the damage is on the replaceable coupons. And in this way, this frame can be used repeatedly. That's where the repeat frame comes, and it's quite a useful tool. We have been using it for multiple tests. And so what was new in this blind prediction? Mainly following the recommendation from 2017 and moving on one more step, we provided the peer yields, mode shapes, and damping ratios to the participants such that they can tune their models to match these and start from that point for their dynamic predictions. And as a second point, we asked the root mean square of response in addition to peak response, and the main reason for this was to basically evaluate the predictions for the entire time tree or time series and not just the peak. And the third item, which is ongoing, is model updating. And as I mentioned, the main essence of blind predictions is mainly to predict the response without knowing the results. But most of us also know that even when you know the experimental results, it's a challenging process to basically obtain them. So in this phase, we are asking the participants what they would update or what they would change when they know the results. And this is an ongoing process, and we hope that this will continue, contribute to the improvement of analytical modeling through the use of blind predictions. And quick information about the contest participants. Mainly, they included practicing engineers and researchers, similar to the participants of this meeting. And in terms of the software, basically the software used included OpenSea, Strand 7, and PISA 3D. And after obtaining the submissions, we basically compared them with the experimental results, and we determined the winning submission. And now I would like to announce the winning submission and the winners. And I can see the smiling faces. Maybe my presentation wasn't as interesting. So yeah, now I will announce the winner. The winner is a 2-member practicing engineer team from Core Brace that includes Chao Xian Li and Brent Saxey. And please join me in congratulating them for their winning submission. And I would like to invite both of them to the stage to receive their plaques and get pictures taken.